Hello everyone. Today we're going to delve into a crucial topic in econometrics. We'll be exploring the applications of the Newey West estimation technique whenever we conduct an OLS regression analysis with time series data. Following our usual approach, we'll be using a practical example drawn from financial research to provide a clear and concrete empirical illustration. Recall that in our previous video, we thoroughly discussed the estimation of ordinary least squares and specifically how OLS regression is effectively estimated through matrix operations. Today, we're going to build upon that foundational understanding.
While this document covers many aspects, our primary focus will be on the accurate estimation of the variance.
Just to refresh your memory, the specific example we discussed earlier was structured in the following way. In this particular scenario, we are dealing with a classic time series regression model. Here, you can clearly see the independent variable represented by the values of x and correspondingly the dependent variable, which are the values of y. For the sake of simplicity and clarity, we've limited our analysis to include only 5 distinct time periods.
So, moving on from step 8, our next step is to calculate the residuals. This is crucial because it pertains to determining the variance of the estimated coefficient, and that variance is directly influenced by the degree to which the errors deviate from one another.
Increased variability and a higher number of errors lead to a larger estimated variance for the coefficients. This variance of the coefficient specifically indicates that the level of uncertainty in accurately knowing the true coefficient is elevated. Given the presence of errors in our data, it means we cannot be entirely sure if the calculated coefficient is precisely the same as the true underlying one. Consequently, this observed deviation, this inherent uncertainty, is fundamentally created because we do not possess a perfectly accurate or complete model. Though, as we've previously discussed, we've already estimated our statistical model. We specifically determined the value of the constant and the slope coefficient. Once we have these figures, we can then quite easily find the estimated value. And this is precisely the reason why we placed the hat symbol here. And then, if you take the estimated value that our model predicted and subtract it from the actual observed real-world outcome, we can then accurately assess and understand the overall performance of our predictive model. So for example, if we have a specific figure here, let's call it x, and another figure here, which we'll refer to as y, we can determine the optimal regression line by utilizing the ordinary least squares method. However, this line cannot perfectly align with every single data point we have. Consequently, we are going to observe a certain amount of error or deviation at virtually every distinct level of x. The ordinary least squares method, or OLS, fundamentally assumes that errors in our model behave independently. Pause. This means we're dealing with what we refer to as IID errors, specifically independent and identically distributed errors. Pause. Essentially, this implies that the distribution of each error term is precisely the same across all observations, and crucially, they don't influence one another in any way.
Regardless of when you choose to observe it, the fundamental nature of this phenomenon remains entirely consistent.
However, that specific scenario may not always come to pass, and if it doesn't, we might face two significant problems regarding the way errors behave when we are fitting an ordinary least squares regression. The first important point we need to address is heteroscedasticity, and this term specifically refers to the phenomenon of a changing error variance.
So, it's important to understand that the variability or spread of our errors, as we call the error variance, isn't necessarily constant. It actually changes as time progresses. For instance, initially, we might observe a relatively low error variance, but this could potentially increase and become significantly larger as we introduce different levels of the variable x into our analysis. So, this phenomenon is technically known as heteroscedasticity. For example, at one point, there might be only a small variability of error around the line, but then as you progress, it can become much larger. It might not be entirely clear at this moment, but once we apply a concrete example, the chart will certainly be much clearer than what's presented here. So when the variance is changing, for example, like this visual pattern, and specifically increasing over time, that particular phenomenon is precisely what we call heteroscedasticity.
So here, for example, if the error variance or distance from the line is smaller than this part, that means the variance is not constant,
And that is significantly changing with the current level of x. So in this particular analysis, we are clearly facing a significant challenge, which is the well-known issue of heteroscedasticity. Beyond that, a second equally important problem that we might potentially encounter is the presence of serial correlation within our error term. What this fundamentally means is that the individual errors themselves are not independent observations, but are in fact serially correlated with one another over time. So the error in period t can be dependent on the error in period t minus 1.
there's a serial autocorrelation in error.
Should we encounter these particular problems, then the statistical estimation of the variance, whether that's for the constant term or for the beta 1 coefficient, would undoubtedly be biased. So, in this particular situation, the ordinary least squares method will unfortunately give us an inaccurate estimation for the variance of our intercept term, which is commonly known as beta 0, and also for the variance of the primary regression coefficient, which is beta 1. It's quite clear that the initial results will be incorrect. The numerical data in particular will prove to be flawed, meaning we absolutely cannot place our trust in the OLS figures. However, the underlying coefficients themselves might still possess some inherent validity or usefulness. We are focusing on the unbiased nature of the numbers themselves. Specifically, we are discussing the statistical variance, the inherent uncertainty, and the standard error, all of which will directly and significantly affect the t-statistics or the resulting p-value.
The results obtained would be unreliable if we are dealing with heteroscedasticity or serial autocorrelation of the errors.
But the coefficients themselves, despite any potential issues we might encounter, will ultimately remain unbiased. Therefore, the ordinary least squares method will still consistently produce unbiased estimates. So the critical question we must address is how we can effectively fix and correct the problematic behavior of the error term in our model.
Now, let's proceed with the assumption that we have successfully derived the estimated value. Once that is established, then, as I previously explained, we can quite readily determine the corresponding error term for each individual period. We must square the error, as this squaring process is absolutely necessary. Next, we'll determine the product of the error and its value from the immediately preceding time lag. This particular calculation will then provide us with a clear understanding of the autocorrelation. We repeat this entire process for each and every individual time period.
We're focusing on this particular instance, carefully considering the relationships that exist between these distinct elements, then between these other two, and subsequently between this pair, and finally between this last set. We then proceed to multiply these values together, and from that we derive the two primary components and the essential HAC computations.
Now here we have the specific equation that allows us to calculate the variance, and this calculation is performed using the well-known Newey-West covariance estimator. This particular method is designed to address the issues of heteroscedasticity and autocorrelation, which are common problems in time series analysis.
So, based on our current observations, this particular finding is indeed quite consistent with the presence of both heteroscedasticity and autocorrelation within the error term of our statistical model. Now, when we consider the variance of the beta coefficient, specifically as derived according to the ordinary least squares equation,
is equivalent to a fixed unchanging variance and also the error term, which is then multiplied by
X transpose X again.
And the overall value of that product term is completely inverted. So, this formula here shows how to calculate the variance within the OLS model, and this specific term is a constant numerical value. Then, this next component denotes the inverse operation applied to the matrix product of X. And finally, this particular section of the equation will indicate precisely how we need to observe the way the regressor moves. If there is a healthy amount of variation present within the regressor, this directly implies that our capacity to estimate the coefficient becomes considerably more precise. The core idea here is that this particular component, the variance of the error term, is assumed to be constant. Let's pause. However, to approach this more comprehensively, if we intend to determine it using the specific Newey-West method, then our subsequent computation will primarily focus on this crucial part. The symbol S in this particular context refers to the heteroscedasticity and autocorrelation consistent covariance matrix, which is derived from the moment condition.
and this particular value is equivalent to gamma 0 added to gamma 1, assuming, of course, that we are considering only a single lag in the error autocorrelation process. Therefore, just one such lag might be sufficient, and indeed, that could prove to be entirely adequate. If we assume that we have autocorrelation of error, meaning that the errors are correlated with each other at a level higher than just lag 1, then we would consequently need to include several additional terms here in our model. But let's just make it simple and assume that the bandwidth is only one lag of error autocorrelation. Here, the k value will essentially serve to estimate the w, which in this model is simply the weight vector multiplied by these specific terms. Now, the key terms that we really need to grasp and understand are gamma 0, and for our particular case, just gamma 1.
All right, let's go ahead and construct these vectors. Specifically, we're looking at x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. We understand that each individual x, like x1, might represent a set of values such as 1, 2, 3, 4, or 5. However, our goal here is to assemble a complete feature vector. In this particular scenario, we're forming a column matrix, and for each of these x values, we're simply going to add a 1 at the very top of its corresponding vector. So, in order to calculate the product of x and its transpose x, we then proceed to multiply this result by the variable itself. This operation would then provide us with the desired component. For instance, considering the very first example, we observe that each individual element contains a value of 1. When we take the value x2 and then proceed to multiply it by itself, the outcome of that calculation will yield the specific terms we require. So, in this particular scenario, the numerical value of 1 is considered a constant throughout. However, if we take this specific element into consideration, for example, its designation would be the variable x. Then moving on, this other corresponding part would also be identified as x. And finally, this last remaining component would then be expressed as xt squared. So, if we multiply these two terms together, we will obtain a matrix containing these elements. Our primary goal is to calculate gamma 0, which is defined as the covariance of the measurement errors occurring within the exact same time frame. So what we're doing here is essentially setting up the covariance between the moment vector of our variable xt and its corresponding error term. It's important to note that there are no lags involved for x here, nor are there any lags for the error term. This is because our gamma 0 parameter is specifically concerned with the contemporaneous or same time period estimation. This is a matrix that specifically represents the second statistical moment. It effectively captures the complete variance structure of the regression statistical moments, all contained within that identical time period. So, if we apply this specific equation, we've already determined these particular values that correspond to each individual x value. Well, then, we simply proceed to multiply that result by the error squared, taking into account each successive time period, 1, 2, 3, 4, and so on. So, to perform this operation, we simply take the error term square its value and then multiply that resulting figure by the given matrix. Consequently, in this specific instance, the particular element we are examining will precisely represent the error term corresponding to period t, and that value will also be squared. Oh, what we're looking at in this particular instance is the calculation where the error term, which has been squared, is then subsequently multiplied by the variable x, and we'll observe precisely the same operation occurring in this other location as well. The squared value of the error term, which is then multiplied by the variable x.
And what we have here is the error term, which has been squared.
The preceding calculation is then multiplied by the square of the variable x. It's important to carefully consider that we are specifically examining the resulting product of the error term with the corresponding value of x. And this provides us with an understanding of heteroscedasticity because it's essentially a function of the variance of the error term, which is effectively the error squared as a function of the level or as a condition of the level of xt. So once we have successfully determined that for every single time period, we're then able to proceed and combine all those individual elements. For example, this specific element, and then this one, and finally this one, 25, that combination will give us the entire upper part, 13. But this isn't just for a single observation of x, 14, or only one specific data point within a single time period. 18, no, this calculation is designed to apply across all possible time periods. 20, so to get that comprehensive result, we simply add all of them together, 19, and that summation will ultimately represent the final complete value, 17. Let's begin with the first component, which is a term representing the error, and this value is then squared. The top right element then would represent the final outcome, or more accurately, it's the total sum of the error squared, and that specific value is then multiplied by our variable x. And finally, for the bottom right position, that particular element would be the result of summing this specific value across every single one of our observations. So, once again, we are observing the error term, which has been precisely squared in this particular instance. And then, following that, we have this specific component, which is, as we've noted before, the variable x directly multiplied by that very same error term. So this particular one is gamma 0, and now we will proceed to gamma 1.
We are currently in the process of identifying the specific contribution that comes from the lag 1 covariance. So gamma 1 in this context is intended to precisely capture the significant effect of one-period persistence and also the influence of the residuals on the overall uncertainty that arises when estimating the beta parameter. For instance, if our model's residuals display a positive autocorrelation, then the gamma 1 parameter will typically be positive, which in turn significantly increases the variance of our coefficient estimate. So let's proceed to carefully apply this particular equation. Once more, we are consistently utilizing the very same term.
But here we are not just using the x variable by itself, we are using x along with its lagged value.
So first, we have this particular constant value that we previously discussed. This refers to the variable x at time t minus 1, which is the lagged x. That term should represent the current observation of x. And that result is derived from the multiplication of the present value of x and its corresponding lagged value.
And then after we've completed that particular calculation, we'll need to multiply by the...
Our focus is on the resulting product of the error term itself. Consequently, the error term we observe in this particular instance isn't just et, instead it is et, which is then multiplied by its corresponding lagged value. Please observe carefully the particular pattern that is evident in this case. The overall process is quite similar. We simply multiply the calculated error by the x value or by the x squared. However, we're not just considering the error from a single period in this instance. Instead, we're taking both the error from the current period and the error from the previous period, treating them as one combined number.
And these values will incorporate not only the x variable observed in the current time period, but also the corresponding lagged x variable, specifically denoted as xt minus 1. And additionally, this same value will also be evident in this particular context.
So what this implies is that we are measuring the serial autocorrelation error and then observing how that particular error changes or varies in conjunction with a different level of x or with a distinct level of x minus 1. So if you were to continue performing that calculation for every single period, and then afterward we were to aggregate all of those results, the final outcome would be the value of gamma 1.
For instance, the specific element's value is calculated by taking the term et and then multiplying it by the expression et minus 1.
This element should be...
First, consider the variable et. This is then multiplied by the specific lag error that we've determined. Finally, we take that product and multiply it once more by the lag of x.
The fundamental principle remains consistent. However, we will proceed to multiply the value of et and its preceding counterpart, et minus 1, by the current observed magnitude of x. And this particular component, as you might logically infer, will similarly perform a multiplication operation.
We're considering 4 distinct elements in this series: et minus 1, et minus 2, and et minus 3.
xt with xt minus 1. So what does that mean?
It means that if we have, for example, positive autocorrelation, and that happens, and if that serial dependence...
What exactly transpires when there is a noticeable variation in our variable xt? Because in this specific scenario, we are directly comparing the current value of xt with its preceding value, xt minus 1. This implies that such a dynamic will inevitably and quite significantly influence the overall uncertainty associated with our estimated regression coefficients.
It's crucial to remember that the specific variation, x, will directly determine the precision of the estimated coefficients. But if that variation in x is also related to an autocorrelation in the error, that will significantly impact the validity of our statistical analysis. To reduce the variability of x when determining the coefficient, this means that the standard error of the coefficient submitted would be lower if we have higher values.
So once we have determined gamma 0 and gamma 1, we can then proceed to plug these values into the main equation.
And by doing so, we will obtain the value of s.
And with a higher value for s, as you can clearly observe, we will certainly experience a greater variance.
All right, let's put this into action right now, making use of our dedicated website.
I'm going to select a specific time series for our analysis, covering the period from January 2000 to December 2005 on a monthly basis. For our dependent variable or Y variable, we will be using the monthly return of a specific sector. And for our independent variable, which is the X variable, we'll be utilizing the overall market return.
So let's begin by taking a look at the Y variable.
So first we need to carefully select a specific sector. Let's consider, for example, the industrial sector, and then we'll proceed to apply our proposed solution.
Let's select an aggregation method, specifically the median, to ensure that our analysis is less affected by extreme data points or outliers. So in this step, we are calculating the median monthly return for this particular sector. Then we click apply, and that will become the dependent variable or the Y variable that we are aiming to explain. So essentially, we're attempting to explain the industrial sector's monthly return by utilizing the market's monthly return.
So we will now activate Series B.
At this point, we will be applying the monthly return data to every single firm in our system. Consequently, by leaving these particular fields empty, the system automatically includes all firms without further selection. Therefore, we can now proceed to apply the setting.
And we got it. We can identify this particular thing as market return. And for the purpose of clarity, we can designate this particular metric as the sector return.
By scrolling down a bit here, we can easily activate the scatter plot for our Y and X variables. This visual representation will help us quickly identify if there's any clear indication of a relationship forming between them. Considering we're working with a simple regression model that only involves a single independent variable X, this process should be quite straightforward and simple to perform.
So the X variable will be the market, because the market will have an impact on the sector as the market represents the broad return.
The Y variable will represent the sector's return. From this point, we have several convenient options available to us. We can choose to download the image file, or perhaps save it directly to our device, or even zoom in for a closer look.
We can clearly see that our relationship is quite good. Between the market and the sector, they generally move in the same direction, meaning that with a higher market return, on average, we tend to have higher sector returns. Is it a perfect relationship? It is not. We do have errors. Now, looking at this visualization, we can clearly discern that the variance of the error term is not constant across the entire range. This pattern is quite evident when we carefully examine the figure before us. For instance, if you observe this particular section, the spread or dispersion of the error points from the regression line is considerably larger, especially when compared to this other area. So what we're observing here is that the spread or the dispersion of the error terms, that is, how much the data points deviate from our regression line, appears to be inconsistent. This means that the amount of variation in the residuals is not constant as we move along the different values of our independent variable X across the entire range. Consequently, this pattern strongly suggests that we might be encountering a significant issue known as heteroscedasticity. So what we need to do first is simply scroll down the page a little bit. From the various available options presented to us, we are able to then specifically choose the regression-based time series model. And then for the crucial dependent variable, which is commonly referred to as the Y variable, we must carefully make our selection.
The sector's overall return.
We want to provide an explanation for this using the market return. And let's initially proceed to run the regression analysis without incorporating the specific adjustment related to the new West, which we previously discussed. Following that, we will then fit the regression model.
The coefficients will not change, they will remain constant.
If we were to choose the new West, the primary factor that would undergo a transformation is either the standard error or the associated t-statistics, and consequently this would directly impact the p-value, which represents the significance level of the coefficient itself. For instance, if we were to focus our attention on the t-value presented here, we would observe that the constant term does not appear to be statistically significant, primarily because the t-value itself is quite small. However, the market return coefficient is observed to be highly significant. Indeed, it is even significant at a stringent 1% level, and this is primarily because the t-value we see here is quite large. Now, let's observe what exactly will occur if we apply the Newey West correction method for calculating the standard error, and subsequently, we perform the fitting process. Please direct your attention to this specific point. It is highly probable that the value will decrease significantly.
Now, considering the market's overall performance, its value experienced a decline.
We're now in the year 19, and it appears we're reverting, going back to our reliance on oil, but we're doing so completely without making any of the crucial adjustments that are truly needed for progress.
The initial figure stood at 23. This indicates that we observed a rather significant drop. The effect remains quite significant even when we carefully adjust for factors like heteroscedasticity and the presence of error autocorrelation. But nevertheless, in the final analysis, the numerical results were ultimately found to be inaccurate. The true accuracy will only be achieved once we properly control for the standard error estimation, specifically by utilizing the New West approach. Consequently, the errors we identify in our analysis will become substantially more robust. Yes, they will be far more robust and reliable.
As I've already pointed out, if you look closely at the figure, you'll notice that the errors we're observing are not remaining constant. In fact, they are continuously changing. This variation in errors appears to be directly linked to the level of the market return. Furthermore, there's a strong possibility that we are dealing with serial autocorrelation in our data. To address these specific issues, particularly the non-constant errors and potential autocorrelation, we will employ the Newey West method for robust control.
That concludes our session for today. Thank you for listening.